Morning. All right. Any announcements or questions before we get started? And then, so just a quick reminder, so we'll have, looking at the syllabus before the term gets away from us. So we're on week 4, finishing up, obviously, liquids and solids, so we'll look at solids today. And then week 5, we'll start more colligative solution properties. And then week 6, we'll have our exam. So that's when we'll do, right, just like we normally do, review on Tuesday, exam on Thursday, and then there'll be no lab for week 6. There will be inter-chapter questions, just kind of, again, putting that out there so we know where we're going. All right, let's finish up this chapter. And so now we've switched to solids. And so we want to talk about how we characterize solids. And I may have mentioned this before somewhat in class, but basically when we make a new material, right, we have to characterize it, excuse me. And so one of the best ways to characterize it, you know, especially like a new organic compound or organometallic, inorganic compound, is to crystallize it. And so you have to slowly, you know, kind of grow these crystals. And so let's at least kind of look at what happens. And this is just kind of the basics of crystal and X-ray diffraction. And so honestly, like I never learned how to solve like crystal diffraction patterns. And so that depends on like your university and your research institution on what happens. But if you're lucky, there's somebody that is a crystallographer and they are basically like paid to solve crystal structures for you. So that's how it worked at my institution. And so the basic kind of thing that happens is you have, oops, maybe I should pull up a picture, if I can, of an X-ray diffraction machine. Let's see if I can actually find. So it looks something like this. This is a good picture. Can we get this larger though? And so obviously, right, the idea is you're going to shoot X-rays at it, and like right little there, you can hardly even see it, but that is where you mount your crystal. So you like literally, you know, take your little crystal on a spatula or whatever, or maybe you even, you know, pluck it on a needle tip and mount it on this X-ray machine there. So then you have your little crystal sitting in the middle, so now it's ready to get blasted by your X-rays. And so that's what happens. And so you get this interference pattern. So essentially, and we don't care too much about this, we're just, again, appreciating it. So there's constructive interference, and so this adds amplitude. And so this makes like a little pattern, basically. And so kind of this general formula, and honestly, we won't do anything with this formula in the class, but this is just showing, so we have our layers between atoms of molecules and between each layer, so they can calculate this wavelength, and given, right, ND sine of your angle that you're hitting it. Anyways, again, right, we're not going to use that. All that's to say is that's how you get a pretty picture. It's like, yay, eventually. And so if you're super interested in this, obviously you can take much, much higher level chemistry classes and get into solving this, and then that could be your career field, is doing X-ray crystallography for people. And what we want to focus on is at least kind of the general patterns then. And so we've kind of talked about this before, just in terms of ionic compounds. And this is just the idea, especially when allowed to cool slowly. So for example, right, you can get certain enzymes to crystallize, like the carbon monoxide dehydrogenase, right? Eventually somebody had to crystallize that enzyme out to figure out the active site. So you can crystallize a lot of things. Obviously, biological samples are much more difficult to crystallize than like a crystal, a chemical compound. And so obviously when they cool slowly, they tend to arrange themselves in a way to, of course, maximize attractive forces and then minimize energy, right? So that's kind of where we get, this is why sodium chloride has a certain structure, right? Repeating pattern of alternate charges. And so then, again, we get a crystalline solid. And so then what's calculated from your pretty picture from your crystallographer is what's called the unit cell. And so that's just your smallest arrangement of the pattern. So it's usually your molecular formula. So I'll just kind of say usually molecular formula that you would get. Obviously, right in the ionic compound, you get the ratio. So, right, sodium chloride, we know they're in a 1-to-1 ratio from our unit cell, so that would be part of your unit cell is formally, right, 1 sodium, 1 chloride unit. And so these unit cells are, of course, 3-dimensional. So again, it's just trying to give you usually the minimum amount kind of needed, but we'll kind of define how many atoms are in certain unit cells. And then, of course, this is repeated over and over again, so that, again, that's what defines the unit cell, is it has to be a repeatable unit. And so kind of going back to the unit cell, this is where, like, water can integrate. So I'll say how you have hydrates, right? So that means at some point somebody looked at the crystal structure, and that's how we can have different forms of magnesium sulfate, either the heptahydrate, there's also, right, 6 equivalents, 2 equivalents, all sorts of other permutations, or you can also integrate other solvents. And so again, right, repeated over and over so that we would get the macroscopic crystal structure. And all, again, this is saying as it repeats, so you can start anywhere and kind of find this unit cell. And so then we'll look at our little points and where, again, our cells are located. And so for our class, we're only going to focus on like the 3 main types. So we have our simple cubic structure. So let's start with that. And so this one, and this is important for like future problems later. So this one only has 1 atom in the unit cell. I pulled up a bunch of links. And so our characteristic example is actually polonium. There are actually not a lot of simple cubic structures. So I think polonium is one of the few, if not only, simple cubic. Go away. And so what this is, the website that this one happens to be on, so this is a Cambridge Crystal Structure Database. And basically, any researcher, any scientist in the whole world that makes a compound and you crystallize it, now you have your coordinate system, then you submit it to the structural database. So everybody does that. And so here we're looking at polonium. And so it's showing us, right, all the poloniums on all 8 corners here of our cube, right? So there we can see our simple cubic structure. And so right now you kind of have to visualize how we get that 1 atom. So of course, right, you just have kind of 1/8 of each of these in the little corner. And then if we were trying to calculate our edge length, again, kind of hint, hint, for the future, we would see that our polonium, or whatever atom here, so we kind of see it that our edge length, right, is 2 times the radius there. So there's our radius. So that's our edge of our cube. So that helps. And so this is, again, just kind of for your information of packing efficiency. So that just means, like, right, how much is in there. So obviously there's like 50% empty space. Right. coordination number, I have to look back specifically how you calculate it, because it depends like how many like this is seeing, I believe, like each individual one is like seeing 6, but that's not very clear from this structure. Trying to see if I can get maybe a slightly better picture. So yeah, this is a better picture for the coordination number. So this is simple cubic, and so like we mentioned, it's how many neighbors, but then you kind of have to look at it the right way or else it doesn't make sense. And so looking at this cubic structure, right, it's just saying, okay, it has one neighbor there, so 1, 2, 3, 4, and then top, bottom, 5, 6. So that's where it gets the coordination number from. If I remember, well, actually, let me just put a link here so you can look at a better visual on that. So I'll put that in the notes. And so then our next one is bodied centered cubic. And where did mine? Here's our bodied centered cubic. So one of our examples would be niobium. So again, a metal. And so we can kind of see from this picture, again, our niobiums. And so let's go back to this representation here. So of course, you want to point out that now body-centered cubic has 2 atoms in there. So again, that will be important potentially for later calculations. This one tries to show kind of maybe 2 different atoms potentially. I actually couldn't find a good representation of this. Instead, I only found like monometallic things such as niobium, which is all the same atom, obviously. And again, right with 2 niobiums in here, so 1 in the center, as shown in this gold color. And then again, 1/8 of each little atom in there. Oops, now I have too many things going on. And so then coordination number is 8. I was going to try to find a better picture representing that, but I have to come back to that. And then again, relevant for calculations that we might encounter in this class is again our edge length. So now it's 4 times our radius of our atom over the square root of 3. Yeah.
Which radius is that? Which atom?
So it would be this one, and
The center one?
yeah, the one on the edge, not the center, but the edge. But like I was saying, I couldn't actually find one where they were different, so they would honestly all be the same, right? All the radiuses, because I was saying, even though it shows different colors, yeah, it's only just like one element. So I'll put niobium there. And so then the last one of, again, the ones that we'll focus on, because there are many other different types of packing names and cubic cells, but again, you can take a whole class on crystallography and go into all that detail. So the last one is this face-centered cubic. And so again, this is one of those ones where I couldn't find a 2 different atom example in reality, but instead we have aluminum as a good face-centered cubic, as shown kind of here. And sometimes I don't know why I couldn't find a good crystal structure of that one. And so again, relevant points is that our face-centered can now fit 4 in there. And so we can kind of see that with our little atoms here. So again, right, we have our 1/8 of each, so as shown in purple. And then we have 1, 2, 3 halves in there to give us 3. So it's kind of, or 6 halves, right? So 1, 2, and then all the faces. So each face has half of an atom to give us 6, divided by 2 to give 3. Does that make sense? So you can see that. And so coordination number would be 12. And again, now we have, right, our radius, and we're mainly just going to, again, deal with one atom. So I'll use aluminum. And so our radius then, our edge length, of our cube can be expressed as 2 times the square root of 2 times r. And then, again, just appreciate how they kind of get more dense now with our packing. So obviously, right, they get more efficient, and that's where we get into, again, why other crystal structures exist. And I was just trying to get a better picture. I have to hunt all over the place. So this one is trying to show you the 8 coordination number. That's not a great picture. This is a better one. So this is our body-centered cubic again, with kind of our middle one. And so it has your 8 nearest neighbors from this reference point. A little difficult to see though. Yeah, it's supposed to be whichever one you pick, right? It's always coordinated to 8 is what it's saying. Yeah. All right, let's try a math problem. Oh, sorry, not yet. Did I not put the math problem in here? Sorry. Where did that problem go? All right, so this just goes through, again, this essentially. So now it's just words, blah, 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 right, 90 degrees, it's a cube. And then simple cubic again, so that's just detailed information. And then, I apologize, I didn't put the problem in apparently. So let's try our problems. Now we're going to look at copper. So copper crystallizes as a face-centered cubic lattice and has a density of 8.96 grams per centimeter cubed at 20 degrees Celsius. So calculate the crystallographic radius. And luckily we have our face-centered cubic edge length right here. So kind of think about how you would approach this. You have all the knowledge. So just take a few minutes Ask your neighbor for inspiration. So let's hear, what are some thoughts on how we can approach this? Yeah, what are you thinking?
To set up the volume part of the density, you need to take the edge length and cube it.
So you want to find, so let's think about that. So right, just kind of setting up what we know. So we could say, well, obviously we have volume is going to be length cubed for this one. So we could say something, well, volume is equal to 2 times our edge length here, cubed. All right, so that's some piece of information. What else could we do? Or what else do we need? Yeah. Oh, yeah. Excellent. And so then, right, finish walking me through so we're all on the same page. So there's a couple of ways to find like the mass, because you want to find the mass of one atom. And so probably what I would do is, right, well, we have our molecular weight of copper is 63.546 grams per mole, but then we could divide it, right, by Avogadro's number to find 1, but then, right, just like he said, there are 4 of them though, so be sure to multiply by 4 there. And so, okay, now we're starting to put all these pieces together, right? So good, right? We figured out how we're going to get our radius from our volume. Now we can figure out how to relate density to our mass and everything. And so let's do that. And so now we just kind of have to, again, put together what everyone just finished telling us. So, okay, density is equal to mass over volume. I've recalculated our mass as this, right? To get our mass of our cube, of our crystal structure. And, well, let's rearrange our equation, right? We're trying to also solve for volume, so we can relate radius to this, right? We don't need volume. So volume is mass over density.
So that R is underneath the root. Oh, you highlighted it the second time.
Yeah, but no, it's not underneath. Because it's more clear up here, because it's 4r over the square root of 2, which simplifies to that. So yeah, it shouldn't be in the square root there. All right, so then just math time. So, right, plugging in my value for our mass. So again, our molecular weight times the 4 atoms that we said were in there, divided by Avogadro's number to get to 1, and then divided by the density, right? So I'm solving for volume here, or L cubed, or this cubed, right? Depending where we want to substitute. Well, eventually we're getting there. So over 8.96 grams. Just keep your units straight, right? So right now we're in centimeters. So let me punch this in and get our volume. All right, so then we should get something of a volume of 4.71 times 10 to the negative 23rd. And then we're still in centimeters cubed, so still in centimeters. So, right, so then we said this was L to the third, so we could take maybe the cube root of that to start with. That might make it easier, right? So then we can set our length equal to our radius. So I think I'll do that. So take this to the cube root. So now I have 3.61 or 612 times 10 to the negative 8th, and we're still in centimeters now, is equal to our L, which is equal to 2 times the square root of 2r. So then we can just divide. So then I get this for the radius of copper. So 1.27 times 10 to the negative 8 centimeters. So the last bit, so right, we had said that the volume was L squared. So I felt the easiest thing to do was I took the cube root of it. Yeah, well, then you get, yeah, L, and then L is equal to 2 times the square root of 2r, so then just, I divided that. So that's, again, probably like the trickiest math here from this chapter. And we'll probably see something like this on the exam where, you know, you're given a thing, you're given a density, right? And then just kind of piece through what we did. Because really, you're just depending on the symbol, the body, or the face, right, to tell you how many atoms are in there for your repeating units. And then you know how many to multiply it by, right, divide by Avogadro's number to get to 1. And then we have the length relationship to R. So you can figure that out for any scenario. All right, let's move on. And so then your book just kind of wants to re-emphasize and reclassify some things here. So just looking at these crystal solids, and actually we'll kind of get into this a little bit more detail about what this truly means. And so we're just kind of comparing, right, different solids. And so this is talking about, right, molecular solids, basically our covalent compounds. And so mentioning, right, that we have our units, or our molecules, and then they all have relatively low melting points. I'm not sure why they picked ice as an example, but I would think of like other organic compounds, you know, just your general aspirin, or, you know, solvents that we work with, benzene, although we don't work with benzene, but I'm just trying to think of organic solvents. We did see hexane. Yeah, ammonia is pretty low. And so, right, again, thinking about those properties. And then we compared them, especially first quarter, right? We compared them a lot to our ionic compounds. And so it's just reminding us, okay, we had our ionic solids with our formula units, which we remember, obviously, right, cations, anions. And then, right, characteristic of high melting points from, again, our crystal lattice structure. So that gives us our high melting points, right, the brittle, all that. And so then we get into these atomic solids, which I think we'll get into a little bit more detail with the paper that I posted as well. And so we'll look at this, but many of the time it refers to atomic units, so just like atoms. And so this could be, and we can even talk about, I'm not sure really if your book is even that great when it talks about this, because it just kind of mentions, oh, we have non-bonding atomic solids, and it mentions this solid xenon, but we'll kind of revisit this thought with hydrogen. But so xenon, right, so xenon is a noble gas, and obviously, right, you can cool it down, and then it might exhibit different behavior potentially, although I still would suspect xenon is not a conductor. And then obviously, these are going to be held together by dispersion forces, low melting points to say the least, right? That's kind of an exaggeration at this point. And then we'll kind of compare that to our metallic solids in a second, and what this means by this metallic bond. And tend to be higher melting points, though, and then, of course, we'll look at kind of why they tend to be conductive. We'll look at that. And so then we also have our network covalent compounds. And again, I think we'll kind of look at the distinction today, hopefully, maybe about what it's trying to get at. And so these would be held together by covalent bonds. So I would, silicon dioxide is in there, but I would also put in there, you know, diamond. So just a repeating covalent structure. But again, we need to look at what this really means. And again, blah, blah, blah. So quick overview, just like we said, ionic crystals, right, dictated by Coulombic attractions. Our molecular crystals were mainly van der Waals, like we went over in this chapter. And then we'll kind of save these network crystals and kind of what this means by this extended network of covalent bonds. Same thing with these metallic crystals. So we'll look at this delocalized orbital, but again, we'll get into it. Okay, blah. I think that's pretty much sums that up. And last little bit before we get into valence band theory is just this colloidal mixtures. We should just define it in this class because we haven't. And so colloidal mixtures are when you have particles, and usually they're going to be on the nanoscale. And so they're just large enough to scatter light. And so this is called the Tyndall effect. And so this is, so unfortunately, right, this is just a picture, or else you'd be able to see what it truly means. So when you have a colloidal dispersion of like a liquid, it would be like shiny, and you would hit the light and you'd see all these little like, you know, shininess. But you've seen it in real life all the time without even realizing it. And so for example, you know, like you go home and you smack your couch and, you know, the sunlight's coming in and all the dust flies up. Or, you know, if you like smoking and, you know, afterwards, woo, your smoke goes in the sunlight, it looks all cool, right? It's all reflecting all the particles. Well, that's the Tyndall effect. And so, right, same thing, just small particles that can refract the light. And so some examples, so again, we can have like a gas-liquid dispersion. So that would be like fog. Luckily, the fog is kind of cleared up, but over Christmas, right, it was pretty foggy. And again, right, all the water molecules are scattering the light everywhere, so it makes it difficult to see. So, right, gas solids, like I mentioned with our smoke or dust particles. And then we have other just formal mixtures, such as like whipped cream and shaving cream. So that would be another colloidal mixture. You can have liquid-liquid, like mayonnaise, liquid solid, so obviously the golden water, but many other, right, paints, pigments, all that. Solid gas, so that would be a pumice stone example. Solid liquid would be like gelatin and cheese. And of course, solid, right, little impurities give rise to colored gemstones. Now I forgot why I had this micelle in here. I think I was just excited last year and wanted to talk about like dissolves like more and how soap worked. Huh? Is it in the book? Yeah. Well, yeah, so I think it's in the book, right, in this chapter, which is why I threw it in there. I don't look at your book regularly. But we can look at how a soap works. Do people know what soaps are made out of? Yeah.
Typically, they're based with they have a polar head and a non-polar head, or hydrophobic and a hydrophilic head.
But then, do you know what, like, where the hydrophobic part comes from? Nobody does any soap making on the side? Yeah, and oil, right? So your non-polar hydrocarbon comes from any like oils or fats, right? So obviously it could be animal fats or olive oil, blah, 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 blah. And so if you want to get into soap making, there's all sorts of calculators that help you get the correct ratios because obviously every fat has different oils. But basically, right, you mix your oil with some sort of base. And so now for manufacturing purposes, they use sodium hydroxide or potassium hydroxide. Back in the day, that's why it was called like lye or soda ash, but they would take like literally, right, what they had burned from the fire. So that was your soda ash, and then you go to try to make soap with it. Obviously, that's also why like soap usually back in the day was kind of harsh because they didn't have good chemical ratios, so you just kind of go for it. But that is, though, how we synthesize this little group here. So then we get our polar group from our soap. And basically, right, we have our carboxylic acid becomes our soap. And so, yes, kind of the long and short of it is you have your polar group. That's some sort of deprotonated carboxylic acid, generally chained to whatever fat there. And so then, of course, right, it works because obviously half of it is solubilized by your water, and then your grease gets trapped up in this nonpolar group. And then it mentions, right, you can form these little micelles then, which just means you have like a little grease ball in the center, right, surrounded by all this soap essentially encapsulated, and then it just can, right, wash away then down your drain. All right, valence band theory. I might go slightly over lecture, but I'll try to finish it. And so we have this band theory, and so let's get into it. So basically, and this is, let's look at sodium, or let's pretend that we're looking at sodium with our 3s here. And so basically, right, it's saying, okay, let's look at some sodium atoms, right? They're brought together. And so now we're kind of thinking more of our atomic C here of electrons. And so obviously we know that our sodium has a valence electron in our 3s1, right? And then there's only one electron. And so basically the oversimplification of this and what this is saying is, okay, when n atomic orbitals combine, and usually you think about it as Avogadro's number, but basically we produce obviously half bonding and anti-bonding. And then if we only have one electron, right, we're always going to fill in the bottom one first. So basically, for our sodium, right, we have our 3s kind of bonding here. And again, all these like little delocalized bands because it's a whole ton of them at the same level, right? So that's what it's trying to show here, that they're all at the same level. So, and they're all half filled. And then we have, right, our anti-bonding, which is, of course, unfilled. And so then now we can get into, again, kind of the basics. And so basically, we have what's called our band gap. So it's always, and you're always examining your HOMO-LUMO gap. So your highest occupied versus your lowest unoccupied. And then essentially, right, for these middle ones, I actually don't like your book's representation. It's honestly so simple that you're going to miss stuff. But basically, right, we're saying, okay, if this HOMO-LUMO gap is relatively small enough, right, our electrons can pass through, and yay, that's why it's an electrical conductor. And so that's what's shown here. So, right, this is the basics that you want to understand and take away from this. Is, okay, if I have a conductor, there's basically no energy gap. Electrons are free to move between our valence and conduction band. And remember, this is just empty. So there's nothing, right, that's just your LUMO. It's just that now they've redefined it as your conduction band. And so that's our conductor. And then a semiconductor just means that we have a small energy gap. And right, we can list characteristic materials like silicon and germanium. And likely this is due to some right SP mixing overlap. And we can also talk about like doping, not with drugs, but right, that's where they replace atoms with other atoms like silicon with either like boron doping or phosphorus. Not quite sure off the top of my head, but right, they change it just a little bit to alter this band gap, right? Make it slightly bigger, make it slightly smaller, depending on what you're trying to do. And then an insulator obviously has such a large energy gap that none of these electrons can ever jump to our LUMO, or as redefined in here, right, our conduction band. And, okay, before I go off on a deeper tangent, other things we should just appreciate. So crystal, right, again, nice, organized arrangement. And that's all that's shown here is like, yay, they're nice and orderly. Obviously a liquid, right, they're going to be flowing. Disorder. Smectic is when they're arranged in these like orderly layers. And again, it would depend on like the material that we're talking about. So we can kind of at least somewhat relate it to graphene in a second. And then we also have nematic, where they're aligned, but then there's no defined layers. And so again, this is just examples of how things can exist and crystallize. But let's get into valence band theory just a tad deeper. Oh gosh, of course, now can I find the paper? All right, so I posted this paper under week 4, and I think you should look at it just because, like I said, your book gives such a cursory overview that I don't really feel like you really understand it. And so let's go through what it was saying and kind of the distinction between these atomic orbitals and then looking at these network covalent models. And so again, I highly recommend that you read the paper. But let's just start here with kind of the simple stuff. I'll try to break it down as fast and as quickly as I can. And so right with our atomic crystal theory, so again, we're just looking at right each individual atom and its orbitals. And so helium, right, we see that, I can't draw on this PDF, at least I don't think I can. But obviously, you know that helium has 2 electrons in it. And so it's basically saying that, right, this would be completely filled up here with our bonding and anti-bonding, right? So kind of back to why helium diatomic doesn't exist. And so it has our completely filled gap here. And then this is much too large. So helium is an insulator. Okay, we're still following. Lithium, right, was basically from our textbook. This is what we had said. Okay, yeah, it just has 1 valence electron. This time now we're looking at the 2s. If we have n number of them, right, we only have 1 electron. So half of them get filled. And then we have, right, our nice gap here. So our 2s anti-bonding is completely open. And so we have our little valence gap. So yay, happy conductor, right? So lithium's a conductor. So then let's move on to beryllium. So a little bit different, right? So, okay, well, it has 2 electrons in the 2s, right? But except it has a little bit of overlap, and that's what's showing here with the higher energy 2p orbitals, right? So they're available, they're vacant. And so because of some mixing here, right, now these electrons can jump up to this 2p antibonding, and yay, right, beryllium is still a conductor like we know. And so then blah, blah, blah. And so here's where things start to break down when we start kind of talking about things. And so now what they've done is they said, okay, let's examine this for carbon. So carbon we know is an insulator. And so here it treats it as just our atomic orbitals, right? So just a bunch of N's like we did before. Except from this prediction, because right, again, carbon, 4 valence electrons, we have p orbitals that can hold 8. So ultimately, right, it's half filled. So this is suggesting that carbon is a conductor. Well, that's not true. And then it tries to treat it with this other approximation. So it says, okay, let's not treat it like such, right? Let's treat it that carbon, yes, we know it sp3 hybridizes, and again, it should be half filled here. Well, neither one of those is true. And so then, right, this is where we kind of have to figure out is, are we treating something as basically a molecular crystal, and now we'll look at the distinction, or are we treating it as an atomic crystal here? And so now this is kind of interesting. So now we're back at hydrogen, which I had mentioned. And so we have our hydrogen. And so now it does two different things. So first it treats hydrogen as H2, right? So how we know it exists as a molecule, right? Diatomic. So that's what's shown here. So we have our bonding and anti-bonding. And so then, right, this is showing that it is an insulator if we treat it as H2. And then versus if we treat it as atomic solid hydrogen, then it predicts hydrogen would actually be conductive. And so there are, not to get down too far the research rabbit hole, but yes, right, this is kind of considered a cool research areas, like could you synthesize metallic hydrogen? And I think some people suspect that metallic hydrogen exists. I forget if it's on Saturn. I want to say it's the planet Saturn. But yeah, so there's, right, potentially evidence for that.
What conditions makes like metallic hydrogen more likely on like places like Saturn?
Ridiculously high pressures. I would have to look back at like what it was referencing and what they calculated, but yeah, like essentially extremely
Because it's
high.
a gas giant. Right?
Yes, and then it has to be like so compressive, right, that it's not going to want to be in a molecular state, but rather an atomic state, which is pretty, I mean, strange for us to fathom. Okay, so then let's get back to carbon and what we're trying to prove. And so now let's look at diamond versus graphite. And so diamond is an insulator versus graphite is a conductor. And so now let's explain why. And so it's kind of confusing is, right, they do this different treatment of it. And so you basically have to treat it as these reduced orbitals, and you're looking at your interaction, obviously, right, your center carbon compared to, bonding with 4 other ones. So, right, looking at 5 total. And so basically, what we're showing here is, okay, again, right now they're all bonded in these sigma orbitals, right, sp3 head to head. Then they get completely filled up, and then we have too large of a gap between our sigma bonding and our sigma anti-bonding. And so now that's showing, okay, diamond is an insulator. But now let's look at this for graphite. And this is a little tricky here too, but I think you all can follow. So, okay, now we're looking at graphite, right? So graphite, sp2 hybridized. And then you have to think about, okay, it has those interactions. right, with 3 carbons. But then we can't forget about, right, our P's here. So, right, our not mixed P's. And so that's what's over here. And then what's also kind of funny, and again, you'll have to kind of imagine with me, although now I might get too excited. Yeah, I'm going to get too excited. So when you take your irreducible representations of everything, so when we normally talk about, right, our pi system, we're only looking at the one combination, right, where they're all in phase and everything is happy. But basically, by math, there have to be 4 combinations. And so that's what's shown. So now, now I lost my paper. So that's what's shown here in the relevance, right? So let's kind of break it down. So we have our sigma sp2 bonds. Well, we don't care about those necessarily. But then we have our 1, 2, 3, 4 pi orbitals, right? And again, I'm telling you that they're coming from our 4 mathematical representations of how these can add. And you'll kind of have to accept that math from me from now. So the lowest one that's filled, right, is going to be the fully symmetric one that we're used to. These 2 in the middle with this little 0 here, that signifies non-bonding. But then we have anti-bonding. And well, basically, again, the long and the short is that we have a half filled, since we have 2 degenerate p orbitals, right? So now we have our 4 orbitals there, half filled, 2 electrons. So yes, we have a small gap here, and that tells us that graphite does conduct electricity. Yeah.
What if it had, just trying to wrap my head around like the gaps and stuff. If that non-bonding orbital was completely filled, would you still have like maybe a less good conductor, but still a conductor because the
Yeah.
between.
I think it would potentially still be like a semiconductor or something. Yeah, if this was completely filled because these are pretty small. But that's where like it starts to get into like the more researchy area, right? Like how big exactly is that
And that's
HUMO?
why there's so much research into semiconductors.
Yeah, and then that goes back into the doping. How can we just slightly change this material, right, to influence the gap or whatever?
How do they experimentally or theoretically find like the differences in between the gaps of like difference between like the gaps of diamond versus the sp3 and the sp2?
Yeah, I'm actually not sure how they do it like in practice. I know a lot of the times like you want to use computational chemistry to compare the energy levels, and that will give you an idea, but I assume you also want to do it experimentally. I mean, they probably test it too, like just passing different voltages, I would assume, but again, I'm not 100% sure how they do that in lab. And then just the last little bit on this paper, and I'll stop yammering, is it's trying to show that when you go perpendicular, though, graphite does not conduct electricity. And so now it's kind of telling you to imagine our potential combinations for how we would do that. So what it's trying to tell you to imagine is like we got a carbon here, and a carbon there, and a carbon there. And obviously I don't have my shading correct, right? So now you can see where you get non-bonding and anti-bonding. And so that's what's shown in this little thing here. And so it's trying to say that it's not conductive for the perpendicular. But again, that's where it kind of goes back to your book, gives a bit of an oversimplification especially here, right? But again, I just want to emphasize you really have to get into, right, what orbitals and the mixing, but that's where the hybridization comes into play. But then also, right, is this material truly this hybridization? Is it acting as an atom? So just a lot of things.
Really cool.
All right. So hopefully you think it's cool and I didn't scare y'all with valence band theory, but I just don't like the oversimplification your textbook gives. But for our class, yes, that's all you really need to know, but when you really get into it, you want to understand it deeper. All right, like I said, stop being overexcited about MO theory. So I'll hand out your quiz. And then, of course, right, you can take a break if you need to. And then I'll hang around on stream. Is there any other last minute questions?
Just had an idea about also maybe doing some research into recycling uranium fuel.
Oh, yeah.
Because I might need that.
I'm trying to figure out like the I was trying to get back to next day, but a lot of them prefer loosely and I'm like, I'm not listening to you. I just definitely don't want to do like
I think I gave them yeah.
yeah.
Okay, everybody got a quiz?
The